Hi, my name is Jasmine. Welcome to another tutorial. Today we're going to be going over a problem called Alien Dictionary from LeetCode. It is classified as hard and was asked by many big tech companies such as Google, Amazon, Airbnb, Uber, and many more. So let's start with reading the problem description. So we have an alien language that uses the English alphabet. Um, and the problem here is the order among the letters is unknown to us. So basically it means that in English we might have A and then B and then C, but in this alien language we don't know the order of these letters. It could be C and then B and then like A. It could be the order of this alien language. Now, we are given a list of strings from the Alien Languages Dictionary. So, where the words are sorted lexicographically by the rules of this language. So, we have to return a string of the unique letters in the alien language sorted in lexicographically increasing order. So, we're given a set of words. And I'll explain it in the algorithm section what it all means. But for now, let's just say all we want to do is we want to find out the lexicographically increasing order, which is like this. It could be something like this in this alien dictionary language. So we want to find this. In English, in regular English, we have A, B, C, and that's the lexicographically increasing order. And if there's no solution, we return an empty string. If there are multiple solutions, we can return any of them. So a string S is lexicographically smaller than than string T if at the first letter where they differ, the string S comes before the letter T. So for example, if we have, let's say, SA and then like BA in this alien language, because S, the first letter, comes before the first letter of the second word, and the lexicographically increasing order, we have S and then B. This is what it means. And if the first letters are the same, let's say we have SM and then we have SC. So if the first letters are the same, we're going to have to check the other letters. Here, the second letter in each word and compare it. So M comes before C, then in our lexicographically increasing order string we have to return, it should be like this, something like this. Now, there are a couple constraints. The word's length, the length of the array that we have is between 1 and 100. Same with each word's length. And the words consist of only lowercase English letters. So for this problem, and I'll show it with an example, what kind of algorithm we'll be using. And the concept we're going to use for this problem is a topological sort, and I'll explain it in the algorithm section as well. So let's actually get into the next section. Okay, as I explained in the previous section, we're going to be using a concept in this problem called topological sort in order to sort the letters of the alien language. And in simple terms, it means a directed acyclic graph is a linear ordering of vertices such that for every directed edge, like U and V, U comes before V, basically. And you'll understand exactly what I mean with an example that I'll be going through right now. So let's say we have this list of words, and we want to find out what's the ordering of the letters for this alien language. Now, it is sorted in lexicographically increasing order, all of these words. So for simplicity, I'm going to convert it to a graph like this. And as we can see, WRT comes before WRF and so on. Now, what we're going to do here, we want to find out the order of letters. As explained in the problem section, we have to first compare the first letter of each word with its next word. So first things first, we're going to compare W with W. They're the same, so we move on to the next letter. It's R, and it's also R in this one as well. Now, this one is T, and in the next word, it's F. So right off the bat, we understand that T comes before F. Now, let's do that again with WRF and EA. So here we have WRF and EA. So the first, right off the bat, the first letters in each word are different. So meaning that W has to come before E. Now, if I want to compare WE with ER, sorry, the E's are the same, so we skip and move on to the second letter, A and R. So meaning that A comes before R. Excuse me. So we have A that comes before R. Now, here in this section, we have ER and ETT. Well, of course, the E's are the same. We compare R and T. R comes before T here. And then with this we compare it to the last word. And here we have E and R. So meaning that E comes before R. So we connect these two graphs, and we have this F here that comes after the T. So we add it here as well. We add it to F. So this is our graph. This is the graph that we get. Let's actually, I actually created a graph here that's simpler and way more neat. So let's actually remove all of these problems. This is the final graph that I drew here. This is the final graph. All right, so now that we found the answer, what is the created the graph? What's the answer for this problem? We need a string that has all the letters in the alien language in topological order. Sorry, and increasingly lexicographically increasing order. So what we do here is we start from W and just move on until we reach the end. So we first have W here and then E. So let's say our first string is W and then E comes after that. But we also have an A which has no dependencies. So we have to bring it before A. Now keep in mind, this is one of the two possible solutions, and we're going to go over the other one. And then after that, we have R. So we have R here, and then T, and then F. So this is the first solution. Now you could also start from A and come to W and E. So first thing we can have A and then W and go over E and then R, T, F. The rest is the same. So this is exactly what topological sort means. And there are two possible solutions for this particular example, and we can return any of them. Now, how do we actually visualize it and make it into an algorithm? Now, we can use a couple tools for that. first things first, we can have a dependency map that we determine the dependencies of each letter, and we can have another table, which is count map. So according to this graph, the graph we created here, A has R as its dependency. Now, we also have W as E's dependency. So because of this, W comes before E. And E is an independency of R, and R has an independency with T, and T has an independency with F. Now, what do we do in count map? We in count map we keep track of all the independencies that we have in this graph, and we actually put it in the dependency map. We keep count of those. So first things first, we have A. Because there's no dependencies before A, we're gonna put 0 here, because nothing comes before A, so there's no dependencies. Now, same goes with the W here. We put a 0 in the count map, but for E, because we have an independency here, W, we're gonna have to put 1. For R, because we have 2 letters that are going to R, we have to put a 2, and for T it's 1, for F is also 1. So this is the count map. Now what are we going to do with this count map? Now keep in mind that we don't have this string yet. We want to find the strings from these 2 maps. Let's say, let me just actually erase this one. We don't have these answers right now. We want to find these. This is our solution. So what we do here, we're going to use these 2. We have a queue here. This is how we're going to use these words, actually find the string. So what do we do exactly here? First things first, we're going to look at the count map and find all the letters that have 0 independencies, like A and W, and put them in the queue. Now we can start from each of those. I start from A, so I have A and then W. Now what do I do next? So I pop A out of the queue here. I pop it out of the queue and put it in our answer string. Now, since I pop A out of the queue, we're going to look at the dependency map and see what are the dependencies of A. It's R, so we look for R in the count map, and since it is one of the R's dependency, we're going to actually decrease it by 1 because one of them is gone. Now, what do I do after that? We actually put W in our answer. Do the same thing with W as well. And we're going to look at W's dependencies and dependency map, and it's E. So we're going to actually decrease E, and it's going to give us it gives us 0. So again, we look at the count map and we add the letters that have count 0, which is now E. So we add E to the queue as well. So this is E. We repeat the same procedure here. Add E and then look at the dependency map. Well, it's R, so we're going to actually decrease R again. We're going to decrease R and add it to the queue because it's 0 now. The dependency counts of it is 0. And then what do we have here? And for R, we actually add, I don't know why we had to add E to this here. And then we have R, pop it out of the queue. And look at here, what is our dependencies? It's T. And we have to decrease it again here. And it's 0. We add it to this here, T. And okay, so what is T's independency? It's F. By the way, sorry, I forgot. We have to add T to the string here and then pop it out of the queue and then look at its dependencies, which we know here is F, and decrease it by 1, add it to the queue, and repeat the same thing. Add F, and it's our last letter. There's no remaining letter. Now, if I did this and instead of putting A, because we have, at the beginning, we have 2 letters that have 0 dependency on count map, I could have picked W first and then add A. It would have been WE and then A. The rest of it is the same. We had the string WEARTF. So this is the general solution for this problem. We can never have, keep in mind that we can never have a cycle in our graph like this. Let me give you an example. If this is our word list, if we have Z, X, and Z again, it forms a cycle. Z comes before X, and then X comes before Z. Now here we have a cycle, and we can't have that. Why? Because our count map says Z has 1 dependency and X also has 1 dependency. None of them are 0, so we don't know where to begin. We can't add it to the queue, and also the count map will never be 0. Like here we have all of them equal to 0, none of them, and our count map is basically empty. But here we'll never achieve that, and also we'll never add anything to the queue because we have to start from letters that start at 0. So that's why we can't have that. Let's actually examine how to implement it in code in the next section. Okay, so let's examine the code for this problem. First, we have our main function alien order. It's a good practice to catch unforeseen errors beforehand. So if our word's length equals 0, we have no answer, obviously, and we return nothing. Now here we have our data structures, dependency map, and count map. And here we have a function. If you notice, we have a couple functions, build graph and BFS, instead of like putting it all here in alien order. It might increase the runtime a little bit, but overall, if we create functions for blocks of code that are a little complicated, it doesn't increase the complexity. It might increase the runtime a little bit, but it makes your code readable, and it doesn't increase the complexity. So it's a good practice. And so we have this function build graph, which takes 3 inputs, our data structures and words, and returns a boolean. It's called success. So we want to see if we can build a graph, and if we can, we return true, and these dependency and count maps will be filled with proper values. Now, if we can't build a graph, obviously we have no answer, so we return nothing. And ultimately, after building a graph, we run a BFS as explained in the algorithm section. We have a queue, we run BFS, and then we return a string this BFS function returns a string, which is our answer. Now let's actually first examine build graph function. So it takes 3 inputs as discussed. And first we initialize our count map. So what we do is like we loop over all the words in a words array, and then we put each character of each word into our count map. We initialize the numbers, the number of frequency with 0. So this is for initialization. And then this section, this for loop, what it does is actually compares each word in our words array and see attempts to find the order of the letters. So what we do here is we loop over our array, and then if these are 2 special cases. We first run these, and then we examine our main possibility. So if the 2 words are equal, as explained earlier, we skip it. It doesn't give us any information. However, there's a special case if our current word starts with our previous word. We have no answer. We can't build a graph. So here, if, for example, I have ABC that comes before AB, I can't build a graph. C comes before nothing. So obviously it doesn't give us anything. We can't build a graph. However, if none of these cases are true, what we do is we're going to compare each character of the current letter and previous letter and find the orders of the letters. So we loop over we store the character from our previous word in first char and from our current word in second char. We compare these 2. If they're equal, it doesn't give us anything, so we continue. Otherwise, we're going to do this. If the first char isn't in our dependency map yet, we are going to add it to our dependency map, and we're going to add first char to the dependency list of the second char. Now, here's the thing. If it's the first time we're adding second char and first char to our dependency map, the add method is going to be successful, and also is going to return a boolean, true. So we put it in this if, and if it's true, we're gonna increase the number of dependency for second char on our dependency map. For example, if we have, let's say, ABC and then we have ABD, then C comes before D. So in the dependency map, obviously the number of dependencies for D will be increased from 0, for example, to 1. And here we're going to add C to the list of dependencies of D. Now, after that, after we create our graph, we return true and move on to the BFS section here. So what we do is, obviously, we build a queue, as explained earlier in the algorithm section. We're going to loop over, we create a queue, and then we loop over our count map and see if we can find characters that have 0 frequencies and add them to the queue. Now, we use result, a string builder result, to store the final string. The reason for that is it's easier to manipulate and add characters to it. Now, while our queue isn't empty, we're going to pull the frontmost element called C from the queue, and then obviously we're going to remove it from count map. By the end of the algorithm, it should be empty if we have an answer, and we're going to add it to the final result string builder. And here, if our C character is a dependency of another character, isn't a dependency of another character, we're going to continue our search. However, if it's a dependency of another character, we're actually going to first decrease the number of dependency for that character, which is called next here. And then if that character's frequency equals 0, we're going to add it to our queue. Otherwise, we're going to skip. So this is, by the end of it, we should have a final string, and our count map should be empty. If it isn't empty, we have no answer, as explained earlier, and we return an empty string. However, we return, if we have an answer, we return the results string, and we convert it to a string, and we return it. And this is our answer. So let's actually submit the code. So it was submitted and successfully submitted. So the time complexity for this algorithm is O of m times n. And the reason for that is n is the number of words and m is the number of characters in each word. We have, since we compare each word, each two consecutive words, and check them character by character for a mismatch, we're going to have O of m times n as our time complexity. We also have a topological sort, which has a complexity of O of d plus n, and the reason for that is d is the number of characters in the alphabet, and n minus 1 is the number of edges. So the overall complexity for that part is O of d plus n minus 1, or O of d plus n, but the overall time complexity for this algorithm is going to be the sum of these two, which is going to give us O of m times n. The space complexity is going to be O of d plus n, and like I said, d is the number of characters in the alphabet, and n minus 1 is the number of edges. So we also have a topological sort section. Since we create a graph, by the way, the time complexity for that part is vertices plus edges. So it's going to be O of d plus n. But we also have topological sort section that we have a queue. That topological sort will take O of d as space complexity, and we have a queue which also takes O of d in the worst case, and the overall space complexity for this part is O of d. But if we sum the last section with this one, it's going to give us O of d plus n as the overall space complexity for this algorithm. Now I hope you learned something from this video, and I'll see you in the next one.